Neural networks have evolved through libraries such as TensorFlow and algorithms such as reinforcement learning. But what are we going to learn about a blue cube and a pixelated squiggle and dog biscuits? Well, actually, let's start out with a little history lesson, some milestones in machine learning. Let's start at 2011 when IBM's Watson built the world's Jeopardy champs. Now, Jeopardy is a tough game because you have to have a deep knowledge of human culture, literature, the arts, science, history. How can a computer do that? An example of a question that Watson got right was a long, tiresome speech delivered by a frothy pie topping. What question would that be the answer to? Watson came back, what is a meringue harangue? Wow! How did it learn that? Well, there was no place where it actually ever saw that. It figured it out from what it learned. Watson was programmed only to play Jeopardy. That's all it could do. It learned culture by reading 200 million Wikipedia pages. 4 years earlier, IBM's Deep Blue program beat the world chess champion Garry Kasparov. That program learned in the same way that Watson did. It deeply learned existing knowledge, not Wikipedia pages for chess, but rather thousands of recorded great chess games. And Deep Blue was so much faster at thinking, it could see more moves ahead, so in that way, it beat the human master. But fast forward 20 years from there, 2017, where the program AlphaGo beat the world Go master. Go is a very different game, much, much more complex. And AlphaGo learned by playing against itself rather than looking through thousands of existing master models. It learned to play in ways that humans had never quite imagined. So the playing against itself means that for each game, one side wins. Well, whichever side wins is then copied and modified through a genetic algorithm. And that becomes a reinforcement learning system where the best models keep getting better and better and better and better till it's better than humans. The current alpha model, Alpha Zero, now can learn the rules of a game itself as long as it knows an end state or sees a score, so it knows it's getting better. It can gain advanced skills in hours that would take a human player months or years. So a common deep learning example uses the MNIST database of hand-drawn digits, hand-drawn numbers, and the TensorFlow machine learning library. So what looks like a squiggle is actually a number 5, but expanded so you can see the individual pixels, and it's divided into 28 pixels high and 28 pixels across, so a 28 by 28 matrix, each one having up to 4 levels of gray. So each digit in the database has over 1,500 bits of information. So this MNIST database contains 70,000 images of hand-drawn digits. 60,000 are used for training the machine learning model. And then 10,000 are held in reserve. After the model is trained and fixed, then those 10,000 are run through to see how well does it perform. So that's a total of 11 million elements for each run. And TensorFlow trains and tests all of this information in under a minute. In creating the model, it identifies and juggles and fixes about 32,000 weights between the neurons in the model. So if you wanted to do that, what programming language would you probably use? This Kaggle survey from 2018 shows that Python is by far the favorite. SQL isn't really a machine learning language. That's for database query. R is sort of in between. Both are very, very popular. The languages you hear about and that are often taught in schools, the C family and Java, together they make up less than half of the people who choose Python. So that's kind of the way to go. And these are free open source programming systems, which is really cool. You can get deep learning libraries for them, again, at no cost. TensorFlow being one from the Google Brain team, Keras another, PyTorch a third. OpenML is more than that. That's a nonprofit organization that has a master database and website. It has over 21,000 data sets, but also examples of how they're used. Great resource. These systems do a lot of what used to require hand coding of the algorithm and optimization of the machine learning. Well, what can be done in 5 or 10 steps replaces hundreds of steps. But TensorFlow, what in the world is a tensor? Well, so a one-dimensional tensor just has a one dimension like length, a 2-dimension length and width, 3-dimension add depth. Well, we can see in 3 dimensions. How about 4th dimension? How do you visualize that? Well, you can see how it's visualized with little blocks adding in. And we can see up to a 6th-dimension tensor. What do you do with a 7th dimension? Maybe you can imagine. But TensorFlow can handle dimensions up to the thousands, like a 10,000 dimension tensor might be used in a typical machine learning algorithm. We can't imagine that. It's not taught in schools. It kind of needs to be so that kids understand some of the fundamentals of machine learning math. So reinforcement learning is actually easy. That's how we learn. So an infant learning to be potty trained might have a potty time poster in the bathroom next to the toilet, and every time he hits the bowl, he gets a red star. This is how animals are trained. You're training your dog, and the dog does something right. It's, good boy, here's a treat, a dog biscuit. But if an adult performs well, it may get a promotion. In sports, home runs and goals. Video games, high scores, awards with Emmys, and you're a valedictorian. You get a Nobel Prize. These are all feedback forms that tell you how well you're doing and give you a way of knowing how you can do even better. So the big ideas from this are that our faster computing and our massive big data sources now have led to unbelievably fast learning for machine learning systems. Machine learning systems have actually now learned how to learn in some cases. And it's so accessible to anybody who wants to learn. It takes a little time, but through R, Python, and the free libraries. There are similarities between human and machine learning. Machines do some things well, humans do other things well. We know that machines are incredibly fast and will always be faster. But it's important for us to realize what humans do well and learn how we can work together.